Hello, my name is Kaylee. I'm doing the presentation for projectile motion for the lab 2 for physics. Some fundamental principles used in this lab were Newton's second law, the velocity update formula, position update formula, and the force of gravity and drag. The purpose of this lab was to compare the position versus time graphs of an experimental and computationally modeled projectile motion with and without drag to emphasize and understand the effect of drag. To do this, we had to experimentally throw something and track it, and then compare that to the computational version with and without drag so that we could see the difference. So the experiment itself, here's the kind of the steps, like outline sort of thing. So we first threw a crumpled piece of paper and recorded it. After inputting the video in tracker and tracking it to create a position versus time graph, the values given is our experimental data, and we can use that to compare a computational model to easily view what drag does to an object in motion. The tracking was done by hand using tracker's default time step of 0.033 seconds. Gravity and drag are the only two assumed forces acting on the system for our computational model. Also, the fact that tracking was done by hand can allow for error, like human error in tracking, so that is something that needs to be accounted for the lab. Here's the glow script code. So it might be hard to see, but on line 66, the b equals 0.0015 is commented out because the code currently is showing without drag, so you can just comment out line 65 and bring 66 as the b equals to account for drag. And here are the actual lines plotted on the graph. So as you can see, the orange line is without drag, so that is the computational model, and it clearly goes way above you can see the other two lines are lower because drag is it's a force acting on it that's not letting it kind of just go on its own. So the experimental and computational versions with drag are very close, and I did this by trial and erroring, getting the drag constant. It took a bit of time to try and do that, but the end result is pretty accurate, I'd say. So what does this mean? So terminal velocity occurs when the net force becomes zero. So the acceleration is zero and the object is falling at a constant speed. One of the questions we had was, do any of the models predict terminal velocity? And for the gravity-only model, the answer is no. For the gravity and drag model, it's possible, but not easily viewable because our object is only in the air for a very short amount of time. So in order to show terminal velocity, just throwing the object with more force would allow it to be in the air longer and potentially give us a more clear image of terminal velocity. Next is what if. So what if the object is thrown up straight, the same initial speed, and then the answer I had is throwing it up straight would take longer than the original angled throw. With the same initial speed, throwing the object straight up gives a larger vertical component than the angled throw, and since the air time depends on vertical component, throwing it straight up would stay in the air longer. With drag, the object loses energy faster and the motion isn't perfectly symmetric, but throwing it straight up produces a longer time to hit the ground than the original throw because it starts with the full initial speed in the vertical direction. And that is it. Thank you for listening. Have a great day.